Hello, this video is going to show how we can achieve functional safety using the Renesas CS IDE. Now, this is the Renesas CS IDE, and I've created a simple project here for an RH850 microcontroller. Let's check we can build the project. So I'll do a rebuild. That's good. So what I'd like to be able to do is to analyze my source code that I've got here. And I want to be able to see, well, first of all, is it compliant to the MISRA C 2012 standard? I'd like to be able to measure a number of metrics on the code, such as calculating or measuring the cyclomatic complexity for each function. I'd also like to be able to execute the code on the simulator, and as it executes, I want to be able to find out, well, how much of this code have we actually exercised? We probably won't get 100% coverage, and so I then want to be able to do some unit testing where I can then give this the appropriate values so it does exercise the rest of the code. Let me close this down, and we'll go to the LDRA launcher, and let's find the project that we've just closed. So in this particular case, this is the one. Let's open that. We can accept the name of the project. I'm going to analyze the files as a system. I want to analyze this particular configuration, and there I want to include the two source files that we've got here. Right, I can now open this project inside TBvision, and I can perform the analysis. This is now going to do a deep analysis on these source files. As we've seen, it's set here the MISRA C 2012 standard, and it's doing a number of different analysis phases. At the moment, it's just done the complexity analysis, where it's measured a number of metrics on the code. And finally, we've generated a number of reports. So let's take a look at the results. So first of all, let's go and view the code review. And this code wasn't written to be compliant to MISRA, and so we have quite a few violations. Let's take a look at a simple violation here. Literal value requires a U suffix. Well, that's very easy to fix. I just need to insert a U here, indicating this is an unsigned number. Well, that's something we can do later. Next, I'd like to be able to look at the quality of this code. So let's take a look at a call graph. And the call graph is going to show us all the functions, and we can see how they're interconnected. And it's also color-coded in blue to show function pointers and green to show the system calls. Okay. A number of different modes I can put this in. We could show a mode that shows all the metrics that give us an idea of testability. Alternatively, I can do the same for clarity, or I can do it as a clarity, or I can do it for maintainability. And one of the most important metrics for maintainability is the cyclomatic complexity. And I can sort and rapidly find the most complex function, and that is this one, integer to ASCII. So let's take a look at a flow graph and get an idea of the graphical representation of the code. So there we can see we have the flow graph. And if I click on a particular block of code like this one, we can see it corresponds to this block over there. If I was to click on this block, we see it corresponds to this one here. In the same way, I can click on a number of branches, and so that's the branch from here down to there. Right, next I want to be able to execute the code on the simulator, and as it executes, I want to be able to measure the coverage. So let's perform the dynamic analysis. So first, it's going to generate the instrumented files. So it's instrumenting the code, now it's building it, and now it's going to execute it on the simulator, and we're going to capture the output to a file, which we're now analyzing, and that will give us an idea of, well, what parts of the code have we exercised. So once again, we'll go to the system call graph, and this time we'll put this into a coverage view where we can see very clearly the coverage we've obtained. Well, let's take a look at the integer to ASCII function. We have 79% statement coverage, and we can see very clearly we have 3 statements here, 3 blocks that have not been executed. Why not? Well, it looks like we've never had a value less than 180. Also, we can see we have a number of branches here that again have not been executed. So let's do some unit testing in order to be able to complement that coverage. So I'm going to go and invoke tbrun, which is a unit testing tool. And inside here, I'm going to go and open a sequence of test cases that I've previously created for the function integer to ASCII. So there we can see I have 7 test cases, and for each individual test case we're going to be able to see the inputs and the expected outputs. So this particular test case here we can see is giving a value of 1, 2, 3, and so that should exercise the parts of the code we didn't exercise earlier. So let's go and execute this again on the simulator. So this is now it's generated the harness, it's performing the build, and now it's going to execute it on the target, and we should be able to get the coverage. So that's the build done. So now it's executing it on the simulator. Once again, it's going to save the information to a file that we can then analyze. And the good news is all the tests have passed, which means with these inputs over here, we got the expected outputs down here. And now let's take a look and see what coverage we've obtained. So there we can take a look at the integer to ASCII function, and we can see this time we have 100% statement coverage, 100% branch decision coverage, and 100% MCDC. And if we take a look at the flow graph, we're going to see that everything here is green, and so now we've just executed these blocks of code here. Okay, so hopefully that's given you an idea of how we can work with the Renesas C IDE. And if you'd like more information, then please don't hesitate to contact us at LDRA. Thank you.